Hello everyone, welcome back. This is the last lecture and today we're just going to go over the practice final and 2 extra problems I found in the web work. Alright, let's get started. Problem 1 is just an initial value problem. It's a first order differential equation, and since we have a term 3x squared times y, that means this is not a separable equation, so we'll have to use integrating factor. And remember that the formula for, let me just write the problem here, y prime plus 3x squared times y equals 3x squared, and y of 0 equals 6. Okay, and this is called p of x, and this is called q of x. And remember that the integrating factor is defined as the e to the integral of p of x dx. And in this case, it is e to the integral of 3x squared dx, which of course is e to the x cubed. So that's our integrating factor. And then y is 1 over I of x times the integral of q of x times I of x dx, which is e to the minus x cubed times the integral of, what is our q of x? That's 3x squared, and times e to the x cubed dx. Now to integrate this, we need to use u substitution. U equals x cubed, and then du equals 3x squared dx. So this is just e to the minus x cubed times e to the u du. Okay, and that gives us e to the minus x cubed times e to the u plus constant c, and plug in e to the u, which is e to the x cubed, so we get e to the minus x cubed times e to the positive x cubed plus c, and that is just 1 plus c times e to the minus x cubed. And the last thing we do is plug in the initial value, y of 0 equals 6. Now y of 0 equals 1 plus c times e to the 0, which is just 1 plus c because e to the 0 is 1, and that needs to equal to 6. That tells us c is 5. So y equals 1 plus 5 times e to the minus x cubed. All right, so this is the first problem. Essentially, it's just an application of the integrating factor. And if you're wondering why integrating factor is can be obtained by e to the integral of p of x, go back to it's probably the second or the third lecture. I actually gave a proof of the derivation of the integrating factor. Okay, problem 2. Oops. Sorry. Okay, problem 2. A 100-gallon tank is full of a solution containing 25 pounds of a concentrate. So first, let's define something called P. Let's just call it P. P of T be the concentrate or the amount of concentrate in the tank at time t. Of course, t is measured in minutes, and p, the amount of the concentrate, is measured in pounds, just so that we use the same units as provided in the problem. All right, so what does the problem tell us? At time t equals 0, distilled water, it is a full of solution containing 25 pounds of concentrate. So that tells us at time 0, there are 25 pounds of the concentrate. So P of 0 equals 25 to put it into the math language. And starting at time t0, distilled water is emitted to the tank at the rate of 5 gallons per minute, and the well-stirred solution is withdrawn at the same rate. So if the solution is withdrawn at the same rate, that means the solution itself, the volume of the solution itself is kept constant, which is 100 gallons. So there's always 100 gallons of solution in it. The problem is the amount of concentrate is changing because you are emitting distilled water, which has no concentrate at all, but you are pumping out solution that contains the concentrate. Okay, and so this gives us a differential equation dp dt, because there is no emission of concentrate. There is no inflow of the concentrate. So the rate of change of the concentrate is purely negative. It's just the amount of concentrate that's leaving the tank. Now, how much is leaving the tank? We know that 5 gallons of solution is leaving the tank, so we multiply 5. This is the volume of the solution that's leaving the tank. We multiply this number by the concentration of the solution that's in the tank. Okay, and the concentration is just P divided by 100, because P is the amount of concentrate in the tank and 100 is the total volume of solution in the tank. So you divide them, you get the concentration. Okay, so this is, to simplify it, you get P over 20, and this is a separable equation. So you get dP dt divided by P equals 1 over 20 times dt. And of course, you integrate both sides with respect to, I don't mean dt, there's no dt here, but you integrate both sides with respect to t, so you get this. And the left-hand side becomes 1 over p dp, and the right-hand side is 1 over 20 dt. Okay, and let's integrate this. The left-hand side, you get ln of, technically you're supposed to get ln of absolute value of p, but because p physically means the amount of concentrate in a tank, there can be no negative weight. It just doesn't make any sense. So we get rid of the absolute value. We just assume that p is always positive because it represents the weight of the concentrate. So it's ln of p equals t over 20 plus arbitrary constant c. Note that because both sides are indefinite integrals, we only need one arbitrary constant. Okay, so we have the equation. Now we just need to plug in the initial condition, p of 0. So we get ln of p of 0. So p is a function of t here. Ln of p of 0 equals, well, t equals 0 over 20 plus c. And that equals, well, first of all, this equals c. And ln of p of 0 is ln of 25. So we found out what the c is. C is ln of 25. Okay, so we get ln of p equals t over 20 plus ln of 25. Now to get an explicit solution, we need to exponentiate both sides. So we get p of t equals e to the t over 20 times plus ln of 25 equals e to the t over 20 times e to the ln of 25. Now e and ln cancel out, so you just get 25 times e to the t over 20. So that's the final answer here. Oh no, sorry, that's not the final answer. This is just the amount of the concentrate in the tank at time t. Now, of course, you don't have to plug in the initial condition here right here. you can exponentiate both sides first. You get P of t equals e to the c times e to the t over 20, and then plug in the initial condition to solve for c, but eventually you get the same answer. Okay, the problem is asking, find the time when amount of concentrate in the tank reaches 15 pounds. So we just solve the equation, P of t equals 15. 25 times e to the t over 20 equals 15, right? And e to the t over 20 equals, that's 3 over 5. Now we take ln of both sides. We get t over 20 equals ln of 3 over 5. And then t equals 20 times that. Oh, I made a mistake here. This is giving you a negative number. Sorry. Right, this is negative because it's the net outflow. So negative here, that's minus, sorry about that. So we just add minus signs everywhere. ln of p is minus t over 20. And it doesn't really change the value of c, so we get minus t over 20 plus ln that, minus, it's just a minus sign everywhere. Okay. All right, therefore t is minus 20 times ln of 3 over 5. Okay, so that's the final answer for problem 2. All right, for problem 3, determine the critical points. Now, critical points just means f partial x equals 0 and f partial y equals 0. And f partial x equals, taking the derivative, you get y minus x squared. And that equals 0. And then taking the partial with respect to y, you get x minus 3y squared divided by 3. So that's y squared equals 0. Okay, now from the first equation, you get y equals x squared. If you plug this into the second one, you get x minus x to the fourth equals 0. And that gives you 3 answers, 3 solutions. X equals 0, I mean 2 solutions, because x minus x to the fourth is x times 1 minus x cubed equals 0. And that gives you 2 solutions, x equals 0 or x equals 1. Therefore, the critical points are 0, 0, because y is x squared, so just plug this in there and you get 0, 0, and 1, 1. So this function has exactly 2 critical points. Okay, and then use the second partial test to classify each critical point. All right, so let's first compute the second derivatives. Partial x, to take one more x derivative on top of this, you get this equals minus 2x, and f partial y equals minus 2y, and then f partial x partial y equals 1. It's just a constant, right? Yeah, it's a constant that does not depend on x or y. Okay, now let's remember that for the second partial test, we need to determine d, which is defined by this. Oh, what's going on? D is defined by f xx xy times f yy xy minus f xy xy squared. That's 4xy minus 1. I doing this correct? Yeah, 4xy minus 1. All right, now let's just plug in the two critical points. We get d evaluated at 0, 0 equals 0 minus 1, so minus 1. That tells you 0, 0 is a saddle point. And then d at 1, 1 is 4 minus 1, that's 3. Being positive, it can be either a relative minimum or relative maximum. And is a minimum, or whether it's a minimum or maximum, is determined by f partial x partial x. F partial x partial x, 1, 1 is minus 2. That tells us 1, 1, oops, 1, 1 is positive d and negative second order derivative. That is a relative maximum. One thing I want to state here is that when d equals 0, it just means the test is inconclusive. If that happens on a test, for example, if I ask you to use the second partial test to classify some critical point, and it happens that that critical point has d equals 0, then you just state the test is inconclusive. You don't have to do any further work or use any other method to determine whether it's a maximum or minimum. Just leave it as it is. Okay, for problem 4, minimize distance from, find the minimum distance from the surface x plus y plus z equals 0 to the point 2, 1, 1. Now, when you see a problem like this, you want to first rephrase it. Find the minimum distance from the surface to the point is the same as minimizing the distance from some arbitrary point xyz to the point 2, 1, 1 under the restraint that the point xyz satisfies the condition x plus y plus z equals 0. So here's what we want to write here, how we want to rephrase the problem. Minimize the distance from xyz to the point 2, 1, 1. Now that is, using the formula for the distance, that's x minus 2 squared plus y minus 1 squared plus z minus 1 squared under 1 big square root. And under the restraint, x plus y plus z. Now instead of writing equals 1, we write x plus 1 plus z minus 1 equals 0. Because immediately looking at the phrasing of this problem, it practically shouts Lagrange multipliers. So we want to use Lagrange multipliers, and for the Lagrange multiplier method, you have to write the restraint method as some function g equals 0. That's why we move the 1 to the left. Okay, now remember when you're using Lagrange multipliers, you have to find all the partial derivatives and set them to 0 and solve the system. Now, since we have a big square root, the partial derivatives are going to be a little complicated. It's still doable, but it might be a little difficult. But we notice that minimizing the square root is essentially the same as minimizing the stuff that's underneath the square root, because the larger this part underneath the square root is, the larger the square root itself is. So it is the same as minimize x minus 2 squared plus y minus 1 squared plus z minus 1 squared. Restraint x plus y plus z minus 1 equals 0. Right? But let's call this f of x and this g of x. And remember that my argument was that f of x is always the one thing we have to note here is that f of x is non-negative because it's the sum of squares, so it's not negative. And the larger f of x is, the larger square root of f of x is. So minimizing square root of f of x is the same as minimizing f of x itself. Okay, now we have our f and g. We can define the function capital F, which is a function of 4 variables, x, y, z, and lambda. So you get x minus 2 squared plus y minus 1 squared plus z minus 1 squared minus lambda times x plus y plus z minus 1. And let's take the partial derivatives. F partial x equals 2 times x minus 2 minus lambda. And f partial y equals 2 times y minus 1 minus lambda. And f partial z equals 2 times z minus 1 minus lambda. And f partial lambda equals minus x plus y plus z minus 1. And all of that equals 0. All right, so for the first equation, we get lambda equals, right, we don't want to write lambda in terms of x, we want to write x in terms of y. So we get 2x minus 4 equals lambda. Sorry, it's going to be a little bit, it's going to be a little messy here. The layout of my work is probably not great. If this is actually an exam, you want to write out the steps, write out every step in a single line. You don't want to, make everything parallel. Okay. I mean, you don't want to cram everything into one line. Okay, so 2x minus 4 equals lambda, and of course 2x equals lambda plus 4, divide everything by 2, you get x equals lambda over 2 plus 2. And this is 2y minus 2 minus equals lambda, and you get y equals lambda over 2 plus 1. And similarly, this you get 2z minus 2 equals lambda, and z equals lambda over 2 plus 1. All right, plug everything into the last equation. You get, well, if minus this thing equals 0, positive this thing also equals 0. So you get x plus y plus z minus 1. This equals lambda over 2 plus 2 plus lambda over 2 plus 1 plus lambda over 2 plus 1 minus 1 equals 0. Okay, so that's 3 lambda over 2. And then plus 2 plus 3 plus 4 plus 3 plus 3 equals 0. 3 lambda over 2 equals minus 3, and lambda equals minus 3 divided by 3 over 2, that's minus 2. All right, so we have our lambda, and x equals, just plug this into the original equation. If lambda is minus 2, then lambda over 2 is minus 1, so you get 1, 0, 0. 1, y equals 0, z equals 0. All right, and at this point, the distance is minimized. So technically, the method of Lagrange multipliers doesn't really tell you whether it's a minimum or a maximum. It just gives you all the extremums, that's it. But, I mean, in this case, obviously, when you're finding the distance from a fixed point to a surface, the distance can grow infinitely large. So any critical point you find will immediately be a minimum. You can just kind of tell, because it's pretty obvious that you can find points that are much further away. Now, if you want to make sure, just find some other point that is not 1, 0, 0, and confirm that the distance from that point is indeed larger than the distance from this point 1, 0, 0. All right, so that's problem 4 and problem 5. Okay, the integral is 0 to 2 and then 0 to square root of x, and then y times x minus y squared cube dx. Okay, and change the order of integration. To change the order of integration, you need to first you need to graph the region R, and the region R is the region formed by these by the limits of integration. So part 1, changing order of integration. Oh, I mean, this is dy dx. I'm missing a dy here. Okay, so let's first graph the region R. The inner integral is an integral about y, and y is between 0 and square root of x. Square root of x is a function that looks like this. So it goes from y equals 0 is the x-axis, so it goes from the x-axis to square root of x. And x is between 0 and 2, so let's call this 2. Then this shaded region is your R. Okay, all right. So the initial integration was dy dx. So you were going from lower bound to upper bound first, and then go from the left to the right. So now we're going to go the other direction. We're going to go from left to right first, and then from bottom to top. Now left to right, we have the left limit is y equals square root of x, and we have to rewrite this into, oops, this just keeps happening. It just keeps zooming in and out. All right, so y equals square root of x is the same as x equals y squared, because this region R lies entirely in the first quadrant, so we don't really have to worry about the sign here. All right, so this is the same as x equals y squared. So we have the integral from y squared to 2, because 2 is the right bound of this region R. And of course, the integrand doesn't really change. The integrand is y times x minus y squared cube dy dx. Okay, and then we go from, I mean dx dy, because we are trying to change the order of integration. Dx dy. All right, and then we need to find the range of y. Of course, the lowest possible value of y is 0, and the highest possible value of y is right here. And we note that at this is the intersection of x equals 2 and y equals square root of x, so the coordinate of this point is 2 square root of 2. So this is from 0 to square root of 2, because this is the largest value y can possibly take inside this region R. All right, so that's part A. For part B, let's evaluate the integral. You can pick whichever one you want. I'm just going to use the original one, the integral from 0 to 2 and then 0 to square root of x, y times x minus y squared cube dx. Okay. Wow. This is dy dx. I'm not sure if this is a good choice. It might actually turns out that the other one is easier, but both of them should work. 0 to 2, 0 to square root of x. And here you get y times, let's multiply this out. You should get x cubed minus y to the 6th. Here's a formula for a minus b to the 3rd power. A minus b to the 3rd equals a cubed minus b cubed, and then plus 3a squared b, then minus 3ab squared. I think we've covered all the orders. Yep, so that's how I remember it. If you see, sorry, I've got the signs messed up. It's minus 3a squared b and then plus 3ab squared. Okay, so that's x cubed minus x to the 6th, minus y to the 6th, and then minus 3 times x squared times y squared, and then plus 3 times x times y to the 4th, dy dx. Okay, distribute the multiplication, we get x cubed y minus y to the 7th minus 3 times x squared y cubed plus 3 times x y to the 5th, and then dy dx. Integrate this, you get x cubed y squared divided by 2 minus y to the 8th divided by 8 minus 3 over 4 times x squared y to the 4th, and then plus 3 over 6 times x to the y to the 6th. This evaluated from 0 to square root of x. Of course, when you plug in 0, you get 0, so let's just ignore that and plug in square root of x instead. Now the first term is just going to be y to the 4th divided by 2, and the second term is going to be square root of x to y to the 8th is once again x to the 4th, and divided by 8, and then minus 3 over 4 times x squared, and then square root of x to the 4th is x squared. You get 3 over 4 times x to the 4th, and then plus 3 over 6, 1 over 2, that is, once again, you're going to get x to the 4th. Yeah, in hindsight, the other way around might be much, much easier, because when you integrate with respect to x first, y is kept as constant. Yeah. Let me just do that one as well. Okay, now compute this. You get x to the 4th over 2 plus x to the 4th over 2. That gives you a complete one. That's 1x. That's 1 times x to the 4th, and minus this, you get 1 over 4 x to the 4th. Minus that, you get 1 over 8. 1 over 8 x to the 4th dx. Integrate that, you get x to the 5th over 40, evaluated from 0 to 2, and that's 32 over 40. And both are powers of 8, so you get 4 over 5. Right, as I was saying, the other direction is probably a lot easier, and that one is 0 to square root of 2. Let me just copy this, 0 to square root of 2, and then y squared to 2. And that's y times x minus y squared cube dy dx. Let's see, 0 to square root of 2. Right, because y is a constant, so you just leave it as it is. Oh, I mean dx dy. I keep forgetting this. Sorry about that. Dx dy. Because when you integrate with respect to x, y is just a constant, so you just leave it as it is. And for x minus y squared to the 3rd, you just change it to x minus y squared to the 4th divided by 4, because it's just x inside the parentheses, so there's no chain rule at play here. And this is evaluated from y squared to 2 dy. Okay, plug everything in, you get the integral from 0 to square root of 2 of y times, well, first plug in 2, you get 2 minus y squared to the 4th divided by 4, then minus y squared, so that's just 0 dy. Okay, you get y times this, so y over 4 times 2 minus y squared to the 4th. You can, of course, multiply everything out, or alternatively, you can use u substitution that have u equals y squared. To make our lives easier, instead of 2 minus y squared, let's write y squared minus 2 because it's an even power. You can multiply it by minus 1, and u equals y squared. Then, am I doing this right? Yeah, u equals y squared. Then du equals 2y dy. Okay, so this one equals the integral from 0 to square root of 2 of, y squared minus 2, sorry about that, u to the 4th times du over 8. That's u to the 5th. Oh, I'm making a lot of mistakes here. Now we need to change the limits of integration appropriately. U equals y squared minus 2, so this becomes minus 2, and this becomes square root of 2 squared minus 2, that becomes 0. Okay, so that's u to the 5th over 40, evaluated from minus 2 to 0. And you get the same answer, 32 over 40, which is 4 over 5. I think this way is easier because you avoid a lot of the messy arithmetics, and you don't have to compute this 4th power because you can just use u substitution to get around that. So I think this is probably the superior way to go. Okay, then problem 6. Okay, let's just start a new page here. Part A, an equals square root. Oh, sorry about that. So sqrt means square root. If you were confused about the 4 letters, sqrt means square root. For some reason, the latex I typed maybe wasn't correct or something. I don't know. I'll fix that. But either way, so this is square root of n squared minus 5 divided by 2n plus 3. Okay, so for this one, this is actually convergent. I'm kind of judging this hindsight here, so I'm just going to write the limit of n go to infinity. Technically, if an doesn't, technically at this point, you don't really know whether an converges or not, so you're not supposed to use the limit sign. But yeah, sorry. Let's just forget about the limit sign. Sorry about that. Okay. The intuition here is that square root of n squared minus 5, when n gets super large, it's almost, the 5 is negligible because n is so large, and of course n squared is so large, and that 5 is negligible comparing to that huge number. So square root of n squared minus 5 is just like square root of n squared, which is n. But you can't write that mathematically. That's not rigorous. But what you want to do is you want to divide it by n. So here's what we want to do. You want to divide top and bottom by n. Okay, and we are going to use that argument that is n squared minus 5 is almost like n squared when n is large. So here's how that goes. N equals square root of n squared, right? So we can change that to square root of n squared minus 5 divided by n squared. And the bottom is 2 over 1, so 2 plus 3 over n. That's just how you do arithmetics with fractions. Now that we have this, we know that the limit of n squared minus 5 over n squared, and now that's just the limit of n go to infinity of 1 minus 5 over n squared. We know that this limit equals 0, and the limit of 2 plus 3 over n equals 2, right? Because 3 divided by a huge number is very small. Because since we know that these two limits exist and we know the values for these limits, then an converges, and limit n go to infinity an is equals what am I doing? This is 1, not 0. Okay, so this is 1 over 2, right? Because the limit of the numerator is 1 and the limit of the denominator is 2. Okay, that's part A. And part B, we have an equals minus 1 to the n times cosine of 1 over n. This is just a simple observation that the limit as n go to infinity of cosine of 1 over n is 1, because when n go to infinity, 1 over n goes to 0, and cosine of 0 is 1. Cosine is a continuous function, so the limit of that is 1. And an equals a minus 1 to the n times this. So that means it's an alternating series with alternating series is a series with alternating signs. So when n is super large, then one number will be close to 1, then the next number will be close to minus 1, then the next number will again be close to 1. So you get a sequence that's jumping back and forth. So that means it's not convergent. Okay, so that's problem 6. For problem 7, determine whether the series converge or diverge. Problem 6 is the convergence of sequences, and problem 7 is the convergence of series, and there's a difference there. Okay? Part A, and it's this series, n from 0 to infinity of n over 500 n plus 70. This can be done using a simple limit test. The limit of n go to infinity of n over 500 n plus 70. This is just 1 over 500, because what you can do is, let me prove this. What you can do is, this is n plus like 70 over 500, and then minus 70 over 500, and that's 500n plus 70. And you realize that this equals the limit of n go to infinity, n plus 70 over 500 divided by 500n plus 70, and then minus limit of n go to infinity of 70 over 500 divided by 500n plus 70. And the first limit is 1 over 500, and the second limit is 0, so you get 1 over 500. And then by limit test, the series diverges. The limit test tells us that the series diverges. If a series diverges, then the limit of the terms has to be 0. Okay, for part B, we have the sum of 1 over n squared times square root of n. Once again, I messed up the square root for some reason. Okay, for this problem, we need to use the comparison test, and since 1 over n squared times square root of n, sorry, I just realized I made a mistake here. We want to start with n equals 1 because when you have 0, if n is 0, if you start with n equals 0, you get 0 denominator, and that's not good. So that's my mistake. We want to start, what I meant to do was the sum from n equals 1 to infinity. Okay, and when n is larger than or equal to 1, then 1 over n squared times square root of n is smaller than or equal to 1 over 1 over n squared. This is when, and of course, all of that is positive. When n is larger than or equal to 1. And we know that the series 1 over n squared is convergent because it's a p-series with p equals 2. Okay, then by comparison test, this series also converges. Okay, that's problem 7. Now let's look at problem 8. For problem 8, we have the function f of x equals 1 over 2x minus 1, and we want to find the third degree Taylor polynomial. Now you might be tempted to use the formula, use the power series representation of 1 over 1 minus x and just replace x with 2x here. But that is actually, I mean, the power series formula that I talked about in the lecture was actually a Taylor polynomial centered at 0. So here we are looking for a Taylor polynomial centered at 1. That means you have to just compute the derivatives and start from scratch. Okay, so this is f of x, and then f prime of x is taking the derivative, you get, let's write this as 2x minus 1 to the minus 1, and taking the derivative, you get minus 2 times 2x minus 1 to the minus 2, and then double prime, you get positive 4 times 2x minus 1 to the minus 3. Oh, with another chain rule, you get positive 8. And this is minus 24 minus 48 times 2x minus 1 to the minus 4. How I'm getting the coefficient is for each step you are multiplying the new exponent. You're multiplying the exponent. For example, going from f prime to f double prime, you have the original coefficient minus 2, and then you multiply the exponent, which is another minus 2, you get 4, and then by chain rule, you multiply the derivative of the inside, which is always 2. So you get 4 times 2, which is 8. Similarly, here you get 8 times minus 3, and then times 2, so you get minus 48. All right, plugging 1, you get f of 1 equals 1 over 1, that's just 1, and f prime of 1 is minus 2, f double prime of 1 is 8, and f triple prime of 1 is minus 48. So the Taylor polynomial, the third degree Taylor polynomial, let's call that as 3 of x, the formula is f of 1, let me just write out the formula here. F of 1 plus f prime of 1 divided by 1 factorial times x minus 1 plus f double prime of 1 divided by 2 factorial times x minus 1 squared, and then plus f triple prime of 1 divided by 3 factorial times x minus 1 to the third. Plug everything in, you get 1, then minus 2 x minus 1, and that's 8, that's 2, so plus 4 x minus 1 squared. 3 factorial is 6, so you get minus 8 x minus 1 cubed. Okay, so that's the Taylor polynomial centered at 1. The important thing here is that you cannot just use one of the 5 elementary power series representations we mentioned in class, precisely because we're looking for Taylor polynomial centered at 1, not 0. Problem 9. Problem 9 is another Taylor polynomial problem. And this time we want to use it to approximate an integral. Okay, now that I think of it, using a new page isn't really that convenient at all. Okay. Regardless, for problem 9, we want to first find the 7th degree Taylor polynomial for the function f of x equals x times e to the minus x cubed, and then use that Taylor polynomial to approximate the integral. Okay, first of all, e to the x equals the sum from 0 to infinity of x to the n divided by n factorial. That's one of the 5 elementary power series we talked about. And if we have this, that's x cubed. Okay, then e to the minus x cubed can be written as the sum of minus x cubed to the nth power divided by n factorial. Let's clean this up a little bit. We get minus 1 to the nth, and then times x to the 3n divided by n factorial. Okay, and therefore x times e to the minus x cubed equals the sum of n from 0 to infinity minus 1 to the n and x to the 3n plus 1, because we have an extra x here, and divided by n factorial. And therefore, the 7th degree Taylor polynomial is, well, the 0th order term is plugging n equals 0, we get x. And plugging n equals 1, we get minus, and then x to the 4th divided by 1 factorial. And plugging x equals 2, we get plus x to the 7th divided by 2. So that's, now that we have the 7th degree term, this is the 7th degree Taylor polynomial. Okay, so one thing to note here is that 7th degree Taylor polynomial doesn't necessarily mean it contains 7 terms. 8 terms. The constant 1, 2, 3, 4, 5, 6, 7. It doesn't necessarily mean it contains 8 terms. It just means the highest order term has to be x to the 7th. So when you find x to the 7th, you stop. In this case, we only have 3 terms, with the highest one being x to the 7th over 2. Okay, so this is the 7th degree Taylor polynomial, and then we integrate this from 0 to 1. And this is the approximation of, so maybe I should write this. The integral 0 to 1 x times e to the minus x cubed dx is approximately the same, is approximated by the integral of 7 dx. That's the integral from 0 to 1, x minus x to the 4th plus x to the 7th divided by 2 dx. The antiderivative is x squared minus 2 minus x to the 5th over 5 plus x to the 8th over 16, and everything evaluated from 0 to 1. Plug in 0, you get 0. Plug in 1, you get 1 over 2 minus 1 over 5 plus 1 over 16. Okay, to find this, the common factor would just be 5 times 16, which is 80. So you get 40 over 80 minus 16 over 80, then plus 5 over 80. And you get 40 minus 11, so 29 over 80. And that's problem 9. So you just find the Taylor polynomial, you just find the Taylor polynomial approximation of the integrand, and then you integrate the polynomial. All right, for problem 10, so we want to use Newton's method to find the two successive approximations of the solution of the equation x cubed plus 3x equals 1. First note that x cubed plus 3x equals 1 is equivalent to x cubed plus 3x minus 1 equals 0. This is a crucial step because Newton's method is used to approximate zeros of functions. If you have it in this format, then the solution is not necessarily a zero. So you want to rewrite an equation into something equals 0. Okay, so let's call f of x x cubed plus 3x minus 1. And then compute the derivative, f prime of x equals 3x squared plus 3. Now the Newton's method have this formula. Formula for Newton's method. Xn plus 1 equals xn minus f of xn divided by f prime of xn. Okay, our x0 is, x1 is 0. That's given in the problem. So we start with the initial guess, x1 equals 0. And then we just move on from there. x2 equals x1 minus f of x1 divided by f prime of x1. So we plug in zeros everywhere. We'll get 0 minus f of x1, plug in 0, you get minus 1. And then into f prime, plug in 0, you get 3. So that's positive 1 over 3. And x3 is x2 minus f of x2 divided by f prime of x2. So that's 1 over 3 minus, plug 1 over 3 into x. You get 1 over 27 plus 1 over, 1 over 3. So you get 1 over 27. That's 1 over 3 cubed. And then 1 over 3 times 3 is 1, and then minus 1. So plus 1 minus 1. And then plug 1 over 3 into f prime. You get 3 times 1 over 9. So 1 over 3, and then plus 3. Okay, plus 1 minus 1 cancel out. To compute this, multiply everything by 27. You get 1 over, when you multiply this by 27, this is initially 10 over 3, so you get 90. Okay, and 1 over 3 is 30 over 90, so it's 29 over 90. And that's the second approximation, aside from the initial guess, that's the second approximation. Okay, so the last problem is not difficult. It's just a direct application of the Newton's method formula. There are two more problems I want to talk about. They're not on the practice final. There are problems that I saw in the web work assignments that I posted. I just thought, because they are a little bit from the practice problems I did in lectures, I just want to mention them. So these are in web work. I think, I kind of forgot, I think they were in 10.4. Let me make sure. Is that correct? I think it's in 10.4. Yeah, it's in 10.4. Okay, the first one is for what values of x does the series n from 0 to infinity of x over 9 to the n converges? Um, in the class, we did problems like, does a series converge? Uh, we didn't really say for what values does the series converge. So here I'm just going to go over this problem. We know that the series, this is a power series, or I mean, this is a geometric series. This converges if and only if absolute value of x over 9 is smaller than 1. And absolute value of x over 9 smaller than 1 is the same as absolute value of x smaller than 9. So the series converges when x is between minus 9 and 9. Okay, this is the first problem. For the second one, for what values of x does from 0 to infinity 6x n divided by n factorial converge? Okay, this is a little bit more difficult, but you can sort of get I mean, without doing any rigorous mathematics, you can sort of guess whether this converges or not. Um, for any x, for any fixed x, I mean, for any x, uh, suppose that x can take any value on the real line. So for any x, then 6x is just a number. I mean, it might be a very large number, but it's a fixed number nonetheless, right? So you have essentially the numerator is a number to the nth power, and the denominator is n factorial. So what does that mean? That means for every term, you're multiplying the numerator by this fixed number 6x, but you're multiplying the denominator by a growing number n. So eventually, because n gets larger and larger and larger, eventually this n will exceed 6x and will be larger than 6x. So you are multiplying at that point, you are multiplying the numerator with a fixed number, again 6x, but multiplying the denominator with something that is larger than 6x every single step, and that number is and that factor on the denominator is still growing. So what I guess what I want to say is this intuition alone should tell you that uh, the series converge for any x, because for any x, 6x is just a constant. And when you multiply the numerator by a constant and multiply the denominator by a growing n, that gives you uh, a convergent series. Because so you should probably think of it this way: factorial grows super fast. It grows much faster than a number to the nth power. But of course, uh, you can't write it like that. Though what I just said is not proper math language. So what we want to do is, to prove this, what we want to do is apply the limit test. The limit of an plus 1. When I write an plus 1, I just mean the n plus 1th term in the series, and divided by an. This equals the limit of 6x to the n plus 1, that's too large, 6x to the n plus 1 divided by n plus 1 factorial divided by 6n to the n, 6x to the n divided by n factorial. And that is 6x divided by n plus 1. And this equals 0 for all x in R. Therefore, by limit test, the series converges for all x in R. Okay, so these are the problems. These are the two web work problems I plan to go over. So that is all for today. This is the last lecture. Final is on Friday. It will be released on Gradescope at 12 a.m. Friday and then due 11:55 p.m. on Saturday. So you will have 48 hours. You can start it anytime you want, but once you start, you will have 2 hours to complete it and then upload. I have an office hour. I sent out a message this morning saying that I will host another office hour on Thursday. So that's an extra hour from 6 to 7:30 p.m. on Thursday. That is the last hour. That is the last office hour before final. So please come if you have any questions, and you can if that time is not convenient for you, you can shoot me an email. Just ask questions via email, or if you want to schedule some other time with me, that's also fine. Just send me an email, and I'll also host a Friday office hour as usual. But given the final would have been released at that point, so I will not answer any final related questions.